There is a number sitting on a government website tonight that almost nobody outside a few scientific circles is paying attention to. And that number is the reason I am recording this. The number is 7. It is the forecast value of an index that measures how violently the magnetic field wrapped around our planet is going to be shaken in the next 24 hours. And a 7 on that index means a billion-ton cloud of magnetized plasma, fired from the surface of the sun, is currently crossing the 93 million miles between that star and this rock. It will arrive tomorrow afternoon. The agency whose entire job is to watch the sun has already filed the paperwork, the formal warning, the Geomagnetic Storm Watch rated strong. Welcome to the Cosmic Forecast. I am going to spend the next several hours walking you through, in the most careful and honest way I know how, what that cloud is, what it is going to do when it gets here, why almost all of you are going to be completely fine, and why the same physical process that will paint a beautiful smear of green across the northern sky tomorrow night is the single greatest natural threat to the civilization we have built. Because what arrives tomorrow is the small version. The large version has already happened once in the age of instruments. It just missed us by about a week. And if this is the kind of story you want to understand before it becomes a headline, stay with me. This is the Cosmic Forecast, and we follow the sun every single day, the quiet weeks and the dangerous ones. Drop a comment and tell me where you are watching from and whether your sky is clear tomorrow night, because what I am about to show you will change how you see that light forever. Somewhere over the northern half of the United States tomorrow night, if the sky is clear and you are far enough from the glow of any city, you may look up and see something that does not belong. A wash of green light along the northern horizon, maybe a smear of red writing above it. Possibly, if the storm performs at the upper end of its envelope, a rippling curtain of color in a place that has no business glowing at all. People are going to pull their cars over. Phones are going to come out. Photos are going to flood every social network within minutes of the first sighting. And almost none of the people watching are going to understand that the same invisible force painting that light across the sky is the single greatest natural threat to the modern world, arriving in a version small enough to survive. Because a warning has already been issued, not a guess, not a maybe, not a forecaster hedging on a slow news day. A formal numbered alert from the agency whose entire job is to watch the sun, telling us in plain language that a geomagnetic storm rated strong on the official scale is expected to strike the Earth tomorrow. The plasma that will cause it is not a possibility sitting on the surface of the sun waiting to decide what it will do. It has already left. It is already in flight. As you watch this, a cloud of magnetized solar material, the size of which dwarfs the planet it is aimed at, is crossing the 93 million mile gap between us and the star that gives us everything. Let me tell you exactly what the warning says, because the language matters. The agency that issues it is the Space Weather Prediction Center, the part of the United States government that does for the sun what the Hurricane Center does for the tropics. They watch it every hour of every day. They have telescopes pointed at it, spacecraft stationed around it, ground stations listening for the radio whispers of its eruptions. And when they see a threat developing, they issue what they call a watch, the same word a meteorologist uses when the conditions for a tornado are coming together. 2 days ago, they put one out. A geomagnetic storm watch category 3, which on their scale is labeled simply and plainly strong. The way these alerts work, this one superseded every watch that came before it. It wiped the board clean and replaced everything with a single message. Tomorrow, the strong one arrives. The number they have attached to it is a 7. There is an index, a planetary index, that measures how violently the Earth's magnetic field is being shaken, and it runs from 0, perfectly calm up to 9, which is the absolute ceiling. The kind of value you see during the most extreme storms in the historical record. Tomorrow, in the window that runs through the late afternoon and evening in universal time, that index is forecast to spike to 7. 7 is high. 7 is the kind of number that pushes the northern lights down out of the Arctic and into the skies over places that almost never see them, into the northern tier of states, possibly farther on a good night. 7 is the kind of number that makes satellite operators sit up a little straighter, makes the people who run the power grid start watching their instruments more carefully than they did yesterday, and makes the airlines flying polar routes start thinking about whether they need to adjust. Here is the thing I need you to hold on to for the next several hours, because it is the spine of everything I am about to tell you. A 7 is survivable. A 7 is, in the grand scheme of what the sun is capable of, a manageable event. The lights will almost certainly stay on. Your phone will work. The auroras will be the headline. By the day after tomorrow, most people will have forgotten it happened. That is the truth, and I am not going to dress it up into something it is not, because the cosmic forecast does not manufacture fear out of a storm that is going to be mostly fine. But the storm arriving tomorrow and the storm that could end the world we have built are not different things. They are the same thing, the exact same physical process. A cloud of charged particles leaves the sun, crosses the void, and slams into the magnetic bubble that surrounds our planet. The magnetic field convulses. Electric currents surge through the ground and through everything we have ever plugged into it. That is what happens tomorrow at a level rated 7. That is what would happen in the catastrophe, except in the catastrophe the number does not stop at 7. It runs off the top of the scale. It does not last for a few hours. The lights do not stay on. The satellites do not all survive. And the recovery is not measured in days. Let me give you a sense of the scale we are talking about so the rest of this lands properly. The index running to 7 tomorrow is a logarithmic flavored measure, which means the jump from a 5 to a 7 is not a small step. It is a substantial escalation in how hard the planet's magnetic field is being shaken. Most days that index sits at 1 or 2, barely registering, the magnetic equivalent of a calm sea with light chop. Tomorrow it triples or more. The storms that have actually hurt us, the ones I am going to walk you through tonight, the ones that dropped grids and destroyed equipment, those reached toward the very top of the scale. The 8s and the 9s, and in the case of the worst of them, ran clean off the top of any scale we had built to measure them. Tomorrow is a serious nudge. The catastrophe is a sledgehammer, but they are swung by the same arm, and that is the whole point. The real story of tomorrow is not the storm. The real story is the gap. The gap between how minor this is and how major the same thing can be. The gap between a beautiful night of auroras and a continent in the dark. We have lived through the small version many times. We get the small version every few months when the sun is active like it is right now. What we have not lived through, not once, not in the entire history of the electrified, satellite-dependent, hyperconnected civilization we have spent the last 100 years building, is the large version. The terrifying part, the part that should keep the people who run our infrastructure awake at night, is that we are statistically overdue for it. How can the same force that makes a pretty light show over Michigan also be the thing that could collapse the power grid for half a continent? How can a storm be both completely survivable and an existential threat, depending only on its size and its timing? That is the question this entire video on the cosmic forecast is built to answer. Tomorrow you get the small version. Tonight, let me show you the large one, and why we have quietly arranged our entire way of life to be as vulnerable to it as it is humanly possible to be. To understand the storm that arrives tomorrow, you have to understand the week that produced it, because the sun did not wake up 2 days ago and decide to throw something at us. It has been building toward this for the better part of a week. The sequence of what it did is worth walking through carefully, because every single piece of it is a smaller rehearsal of the catastrophe we are circling. It started around the 2nd of June. A region on the face of the sun, a knot of intense magnetic activity that scientists had numbered 4456, came alive. When I say came alive, I mean it started firing. 5 separate flares in a single day, including one that was already substantial. That was just the warm-up. The real day, the day that tells you this region meant business, was the 3rd of June. In the space of about 10 hours on the 3rd, that one region fired 3 major flares. The first came just after 1 in the morning Universal Time, rated M9. 3. Then around 4 to 7 in the morning, a second one rated M7. 7. Then late in the morning, just after 11, the big one, a flare rated X10. 3 major flares from one spot on the sun in 10 hours. Let me put those classes into terms that actually mean something, because the letters look like alphabet soup if no one explains them. Solar flares are sorted by how much X-ray energy they pour out, and the scale goes up through the letters C, then M, then X. Each step is a 10-fold jump in power. A C flare is a small thing, background noise on an active sun. An M flare is 10 times stronger, the kind that can cause radio problems on the daylight side of the Earth. An X flare is 10 times stronger than that, the top of the named scale, the heavy hitters. When I tell you that region fired an M9. 3, I want you to understand what that number is really saying. M9. 3 is the very top of the M class. It is one tiny step below X. It was, for all practical purposes, a near-miss X flare. That region did not fire one major flare on the 3rd of June. It fired what was effectively 3 of them back-to-back in a single morning. I want you to feel the compression of that timeline, because it is easy to read past it. Most of the time, even on an active sun, a major flare is a notable event, the kind of thing that gets its own alert, a punctuation mark in a day. To get 3 of them, 2 at the very top of the M class and 1 a full X, out of a single region in a window of about 10 hours, is the sun working at a tempo it does not usually sustain. It is like a fault line that produces not one large earthquake but 3 in a single morning from the same patch of ground. Each one drained tension from the region. Yet the region kept reloading and firing again, which tells you just how much stored magnetic energy was packed into that one tangled knot on the surface of our star. Why does one region do that? It comes down to the magnetic field inside it. The sunspot region that did this carried a classification that the people who study these things write as beta gamma delta. You do not need to memorize that. You just need to understand what it means. The magnetic field inside that region was tangled, twisted, knotted up with north and south magnetic poles crammed right up against each other, in ways the sun does not like and cannot sustain. Think of it like a rubber band you keep twisting. At some point, the stored tension has to go somewhere. When a tangled magnetic region on the sun finally snaps, it releases that energy as a flare, and sometimes it throws a piece of the sun's own atmosphere out into space along with it. The most violent, the most tangled regions, the delta regions, are the ones that produce the biggest flares, and 4456 was about as tangled as they come. Here is the part that makes this week different from a week where the sun just flares and nothing reaches us. On the 5th of June, 2 days after that triple flare morning, a geomagnetic storm actually hit the Earth, a real one. Rated G2 moderate on the scale, driven by the cloud of plasma thrown off during the earlier activity. The index that measures the shaking of our magnetic field climbed past 6. This is not theoretical. The sequence we are talking about has already made direct contact with our planet once this week. The sun has already landed a punch. Tomorrow is the second punch, and it is forecast to be harder. That second punch was loaded on the 6th of June. A region fired another flare, an M1. 8, and this time it launched something the forecasters could see and measure leaving the sun. They call it a partial halo coronal mass ejection. A coronal mass ejection, a CME, is the big one. It is the thing that actually matters for storms on the ground. It is not light, it is matter. It is a billion-ton cloud of magnetized plasma, physically blasted off the sun's outer atmosphere and hurled into space. When one is aimed even partly at Earth, it shows up in the coronagraph images as a halo, an expanding ring spreading out in every direction, because it is coming more or less straight at the camera, which means more or less straight at us. We know how fast this one is moving, because the eruption announced itself with something called a Type 2 radio sweep, a kind of rising radio tone that a shock wave makes as it tears outward through the sun's atmosphere. From that, the speed was clocked at around 838 kilometers per second. That is more than 1.8 million miles per hour. An 11-degree-long filament of solar material erupted along with it, a long rope of cooler, denser gas suspended in the sun's atmosphere by magnetic fields that finally let go and flung the whole structure outward. That cloud, launched on the 6th, is the one arriving tomorrow, the middle of the 8th. It is worth pausing on the sheer scale of what a coronal mass ejection actually is, because the calm scientific language hides something almost incomprehensible. When the sun launches one of these, it is not venting a puff of gas. It is hurling a structure that can contain 1 billion tons of matter. A cloud that, by the time it reaches our part of the solar system, can be wider than the distance from the Earth to the Moon many times over, expanding as it travels until it is large enough to swallow our entire planet and its magnetosphere with room to spare. The reason it does not simply obliterate us is that it is incredibly diffuse, spread so thin across that enormous volume that no single piece of it would feel like much. The danger is not that it is solid. The danger is that it carries a magnetic field, and that field, sweeping over the Earth, is what shakes our own magnetic field and drives everything that follows. 1 billion tons of magnetized plasma, moving at more than 1 million miles an hour, expanding to a size that dwarfs the planet. And we track it across space and wait to see which way its field is pointing. That is the thing arriving tomorrow. If you could pull back and look at the whole face of the sun right now, you would not see one lonely spot. You would see a sun that is busy. 9 separate active regions are numbered on the Earth-facing side as I record this, with the big tangled one still the most complex of the group, and others worth watching right behind. The daily sunspot count has been running noticeably higher than the monthly averages we have been seeing recently. This is not a quiet sun catching us off guard. This is a sun that has been loud for a week, and it is not finished. There is one more reading from this week that I want to plant in your mind now, because it becomes important later. Out at the altitude where our satellites fly, the count of high-energy electrons spiked. There is a specific threshold the forecasters care about, 1,000 units of what they call electron flux. And crossing it triggers an automatic alert, because that is the level at which these fast electrons start to cause real problems for spacecraft. On the 6th of June, that flux did not just cross the threshold. It peaked at 1,284. Hold on to that number. When we get to what a storm does to the satellites we have come to depend on for almost everything, that number is going to matter. There was a second particle signal this week as well, and it points at a different kind of danger, one aimed less at machines and more at people. Alongside the electrons, the count of high-energy protons became enhanced after the flaring. Protons are heavier, and when the sun accelerates them to high energies, they become a radiation hazard, the kind that matters for astronauts outside the protection of the lower atmosphere, and in the most extreme events. For the crews and passengers of aircraft flying high-altitude polar routes, where the atmosphere overhead is thinner and the magnetic shielding weaker. This week's proton enhancement was modest, well below the level that would prompt action, the equivalent of a faint dusting rather than a storm. But it is a reminder that the sun's reach is not only electrical. In a truly extreme event, a great solar proton storm, the radiation environment in space and in the upper atmosphere climbs sharply. Airlines reroute flights away from the poles to keep their crews and passengers out of the worst of it, and any astronaut caught outside heavy shielding faces a genuine medical threat. It is one more dimension of exposure, one more system, human this time, that the quiet star can disturb when it chooses to roar. I want to address the comforting thought you might be reaching for right now, the one that says, but is not the sun supposed to be calming down? There is a piece of truth in that, and it makes what is happening more interesting, not less. The sun runs on an 11-year cycle, swinging from quiet to active and back again. We are now past the peak of the current cycle, the one scientists number 25, sliding down into what they call the declining phase. The intuition is that a declining sun is a safer sun. The data tells a more complicated story. By some measures, this cycle has performed comparably to the historically strong cycles of recent decades, even though its raw sunspot count has run noticeably lower, something like a quarter below the strongest of those past cycles. What that suggests is that the activity in this cycle is concentrated in ways the simple spot count does not capture, packed into the high-frequency churning of the outer solar atmosphere, producing significant flares and eruptions, even as the headline numbers say things should be winding down. A sun that keeps firing X-flares and launching earthbound clouds in its declining phase is a sun that has not read the script we wrote for it. Here is the part of that history that should erase any false comfort entirely. Some of the most damaging geomagnetic storms in the record did not happen at the roaring peak of their cycles. They happened on the downslope in the declining phase exactly where we are now. The great storm that took down Quebec, which we will come to in detail, came in the declining phase of its cycle. The Carrington event itself struck as its cycle was waning. There is a reason for this that scientists have studied, having to do with the way the sun's large-scale magnetic structures reorganize as a cycle ages, opening up fast streams of solar wind and producing the kind of long-lived geoeffective conditions that drive serious storms. The declining phase is not the safe part of the cycle. In some respects, it is the dangerous part. The fact that we are past the peak is not a reason to relax. It may be precisely the window in which to pay closer attention. So that is the weak, a tangled region, a triple flare topped by an XA confirmed direct hit on the 5th. A billion-ton cloud launched on the 6th, a sun covered in active regions, a population of fast electrons climbing into the danger zone. A cycle that is supposed to be quieting down and stubbornly refusing to. Every piece of that is the small version, the rehearsal. The same regions, the same flares, the same clouds, the same physics that, scaled up and aimed right, becomes the thing we should genuinely be afraid of. The strangest part of the whole sequence is that even the experts cannot tell you for certain how bad tomorrow will be. Let me explain why. Because the reason they cannot is the same reason the big one is so dangerous. Here is something that sounds like a contradiction, but is the absolute center of how space weather works. The forecasters can see the cloud coming. They can measure its speed. They can estimate its size. They can watch it leave the sun and track it across space. And they still cannot tell you with confidence until about an hour before it hits whether tomorrow's storm will be a shrug or a haymaker. That is not incompetence. That is physics. Understanding why reveals exactly why this hazard is so treacherous. When a coronal mass ejection reaches Earth, it does not simply crash into the planet like a rock into a window. The Earth is wrapped in a magnetic bubble, the magnetosphere, generated by the churning of molten iron deep in our core. That bubble is our shield. It deflects the constant stream of particles the sun is always throwing at us. When a CME arrives, the first question is not how fast or how dense the cloud is. The first question is which way its magnetic field is pointing. This is the single most important variable in the entire science. Let me make it concrete. The cloud of plasma carries its own magnetic field, tangled up inside it from the moment it left the sun, and that field has an orientation, a direction it points. The part that matters is whether it points north or south. The forecasters call this the BZ component. When the cloud's field points north, the same way Earth's field points out in front of our planet, the two fields are aligned. They resist each other, and the cloud mostly slides around the magnetic bubble like water around the bow of a ship. You can have a fast, dense, massive CME, a real monster of a cloud, and if its field is pointing north when it arrives, you get a surprisingly gentle storm. The shield holds. When the cloud's field points south, everything changes. A southward field is opposite to Earth's field, and opposite magnetic fields do not resist each other. They connect. They link up and merge in a process called magnetic reconnection. That connection is like opening a door directly into the magnetosphere. The energy of the solar wind pours in. The shield, in effect, unlatches, and the storm goes from a shrug to a haymaker. Same cloud. The only difference is which way a magnetic field happened to be pointing when it arrived. Here is the cruel part. We cannot measure that orientation until the cloud is almost on top of us. There is a spacecraft parked about 1,000,000 miles upstream of Earth, sitting at a special point where it can sample the solar wind before it reaches us, and that spacecraft is our early warning. That special point has a name, the first Lagrange point, a place where the gravity of the Earth and the Sun balance in just the right way to let a spacecraft hover more or less stationary between us and the star. We keep instruments there precisely so that the solar wind washes over them before it washes over us. It is a clever solution, and a vital one, the closest thing we have to a tripwire. But it has a hard physical limit baked into it. 1,000,000 miles for a cloud moving over 1,000,000 miles an hour is only about an hour of lead time. The forecasters watch the cloud cross space for 2 days, and then, in the final hour, the spacecraft finally reads the magnetic orientation. Only then do they know whether the door is going to swing open or stay shut. Let me slow down on that word reconnection, because it is doing an enormous amount of work, and most explanations skate right past it. Magnetic field lines do not normally just merge. They behave, most of the time, like they cannot pass through one another, like strands that slide and bend but keep their separate identities. When two oppositely directed magnetic fields are pressed hard against each other, as happens when a southward-pointing cloud field meets Earth's northward-pointing field at the front of the magnetosphere, something gives. The field lines snap and splice, breaking and reconnecting into new configurations, and in that violent rearrangement, they fling the plasma trapped on them away at tremendous speed and dump a vast store of magnetic energy into the system. It is the same fundamental process that powers the flares on the sun in the first place, now happening in miniature at the doorstep of our own planet. When the cloud's field is northward, this does not happen efficiently and the cloud is deflected. When it is southward, reconnection runs wide open and the magnetosphere lights up like a circuit that has just been switched live. The energy that pours in does not stay at the front of the magnetosphere, where the reconnection happens. It gets carried back around the planet into the long magnetic tail that streams away from Earth on the night side. And it builds up there like water behind a dam until the tail itself reconnects and releases the stored energy back toward Earth in a sudden surge. That surge is what drives the great electric currents in the upper atmosphere, and what makes the auroras suddenly brighten and dance during the most active phase of a storm. The whole system is a kind of engine, loading and unloading energy. A strong storm is that engine running hard for hours, each cycle hammering the magnetic field at the ground a little harder. This is why you will sometimes hear a forecast for a severe storm and then watch almost nothing happen. The cloud arrived with its field pointing the wrong way for trouble. The shield held. The predicted G4 turned out to be a G1. There is a real example of this kind of disappointment, or relief, depending on how you look at it, in the very week we are discussing. The geomagnetic storm that did arrive on the 5th of June, the confirmed direct hit, was by some early expectations going to be stronger than it ended up being. The cloud came in, the magnetic field strength jumped to several times its normal value, the solar wind sped up, the density climbed. All the ingredients for a serious storm were present. Yet for stretches of it, the field orientation simply did not cooperate, pointing northward when trouble would have required southward. And so the storm delivered a moderate event, rather than the severe one the raw ingredients might have suggested. It found its way to a G2 with a brief touch toward G3, and then it waned. That is the coin flip in action, observed in real time just 2 days ago. I want to be honest with you about this because it might happen tomorrow. There is a real chance that the storm arriving tomorrow underdelivers, that the field points north, the coupling stays weak, and we get a muted event with auroras farther north than hoped and not much else. If that happens, the forecasters were not wrong about the physics. They were right about the cloud and unlucky about an orientation that could not be measured in advance. Space weather forecasting is genuinely one of the hardest prediction problems we have, and the people doing it are working with a fundamental limit baked into the geometry of the solar system. Sit with the flip side of that coin for a moment, because this is where the comfort turns cold. If a storm can underdeliver into a dud because the field points north, it can also overdeliver into a catastrophe because the field points south. Arriving with a strongly southward field that throws the doors wide open and lets the full violence of the cloud pour into the system. The same uncertainty that means tomorrow might be quieter than forecast is the exact same uncertainty that means the big one, when it comes, can be worse than anyone expects. The unpredictability does not just protect us, it exposes us. It means we are always, in a sense, gambling, and the house is the sun. This is where the practical reality of defending ourselves runs into a wall, because the short warning time shapes everything about what we can and cannot do when the big one comes. That hour of lead time from when the cloud crosses the spacecraft upstream to when it reaches Earth is the entire window in which anyone can act. It is enough time, if the systems and the plans are in place, for grid operators to take protective measures, to reduce the load on the most vulnerable transformers, to reconfigure the network into a more defensive posture, to brace for the impact. An hour, used well, could be the difference between a grid that bends and a grid that breaks. An hour is not much, and using it well requires that the plans already exist, that the operators are trained, that the authority to act decisively is already granted, that nobody wastes precious minutes deciding whether the threat is real. The warning is short, and the stakes are total, which means the preparation has to be done in advance, in the calm years before the storm, not improvised in the frantic hour when it is already bearing down. That, once again, is a matter of foresight, of choosing to spend effort and money on a threat that has not yet arrived. The hour of warning is a gift the physics gives us. Whether we have built the readiness to use it is entirely up to us. Now I need to plant one piece of physics before we leave this part, because it is the bridge to everything that follows. When that magnetic door opens and the energy pours in, it drives enormous electric currents high in the atmosphere, rivers of current flowing through the upper air over the polar regions. Those currents, surging and shifting, cause the Earth's magnetic field at ground level to change rapidly, to swing and pulse and lurch. That detail sounds academic. It is the whole game. There is a law of physics, discovered almost 2 centuries ago by Michael Faraday, that says a changing magnetic field creates an electric field, and an electric field, anywhere there is a long piece of metal to carry it, drives a current. The Earth, during a strong geomagnetic storm, becomes a place where the magnetic field is changing fast over a vast area. Draped across that vast area, we have strung the longest pieces of metal in human history. Power lines that run for hundreds, thousands of miles, pipelines, railways, undersea cables. Every one of them is an antenna for the current the storm induces in the ground. Tomorrow, at a level rated 7, that induced current will be a trickle, a nuisance the grid operators manage without most of us ever noticing. The mechanism is real, and it is on, and it is the doorway to the catastrophe. Because what happens when the trickle becomes a flood is the most important thing this video on the cosmic forecast has to tell you, and it has happened before, more than once. And we got lucky every single time. Let me show you what the flood actually does. Picture the longest wire you can imagine, not the cord on a lamp. A high-voltage transmission line, the kind held up by those steel lattice towers that march across the countryside, carrying power from a distant plant to a distant city. That line can run for hundreds of miles in a single span, and there are tens of thousands of miles of such lines stitched across every developed country on Earth. They are the arteries of modern civilization. During a strong geomagnetic storm, they become something their designers never fully intended them to be. They become collectors of the current the storm induces in the ground beneath them. The current that gets induced is a strange kind of current. The power grid is built to carry alternating current, electricity that reverses direction 60 times a second, smoothly, predictably, the rhythm the entire system is engineered around. The current a geomagnetic storm pushes into those long lines is not alternating. It is, for all practical purposes, direct current. It flows one way, slowly, a deep, slow surge compared to the rapid back and forth the grid expects. We call it a geomagnetically induced current. It is poison to the most important and most vulnerable piece of equipment in the entire system, the transformer. It is worth pausing on how invisible and how essential these machines are, because the entire vulnerability hides in that combination. You have driven past hundreds of them and never given one a thought. They do not move. They do not have screens or lights. They just sit there and hum year after year, asking nothing of anyone, quietly performing the single most important translation in the entire electrical system. Taking the very high voltages that move power efficiently across long distances and stepping them down in stages to the levels that are safe to deliver to a factory, a neighborhood, a home. Without that translation, the grid is just wires with nothing useful at the end of them. There are a relatively small number of the truly large, truly critical ones, the extra high voltage units at the major hubs. And the loss of even a handful of them in the wrong places would tear holes in the network that the rest of the system cannot easily route around. We have built our entire civilization on top of a layer of humming gray boxes that almost no one knows exist, that take the better part of a year to replace, and that a solar storm can cook from the inside. That is the hidden keystone, and it is exactly the kind of thing that gets ignored right up until the moment it fails. You have seen transformers even if you have never thought about them. The big gray boxes humming in a substation behind a chain-link fence. They are the devices that step voltage up for long-distance transmission and step it back down for your neighborhood, and the grid cannot function without them. The largest ones, the extra-high voltage transformers that sit at the great hubs of the system, are extraordinary machines. They can weigh hundreds of tons. They are filled with thousands of gallons of cooling oil. They are tuned precisely to handle alternating current and nothing else. When a slow, one-directional, geomagnetically induced current comes flowing in alongside the normal power, it does something to the transformer's core that engineers describe with a quiet, terrifying word: saturation. Here is what saturation means in plain terms. A transformer works by using a magnetic core to move energy from one coil of wire to another, and that core is designed to swing its magnetism back and forth in step with the alternating current. The slow, induced current from the storm pushes a steady magnetic bias into the core, shoving it off-center, driving it, half the time, into a state where it simply cannot hold any more magnetism. The core saturates. A saturated transformer starts to misbehave in every way at once. It overheats, sometimes catastrophically, hot spots forming inside it that can cook the insulation and char the windings. It starts drawing enormous amounts of what engineers call reactive power, destabilizing the voltage across the whole network. It distorts the clean waveform of the electricity into something jagged and full of harmonics that ripple out and confuse the protective equipment everywhere else on the grid. Let me make the saturation a little more vivid, because it is the physical heart of the whole catastrophe. Inside that transformer is a core of specially engineered iron. The way the machine works is that the alternating current creates a magnetic field in that core, which swings cleanly back and forth, north, then south, then north again, 60 times a second. That swinging field is what carries the energy from one set of windings to the other. The iron core has a limit, though, a maximum amount of magnetism it can hold, and in normal operation the design keeps it comfortably below that limit on every swing. Now introduce the slow, one-directional current from the storm. It acts like a thumb pressing down on one side of that swinging field, biasing the whole oscillation off-center, so that on one half of every cycle the core is shoved past its limit into saturation, where it simply cannot absorb any more magnetism. The energy that should have been smoothly transferred instead spills out as stray magnetic flux into the surrounding metal structure of the transformer. That stray flux dumps its energy as heat in exactly the parts of the machine that were never designed to get hot. The structural steel, the clamps, the tank walls, hot spots form. The cooling oil begins to break down. The insulation, which is often little more than specially treated paper, starts to char. The transformer is, in a sense, a carefully balanced thing built to do one job perfectly, and the storm jams a wedge into the balance. In the worst case, the transformer does not just misbehave. It dies. The heat builds faster than the cooling can carry it away, and the insulation fails and the machine is destroyed. Not tripped offline, not switched off to be turned back on later. Physically, permanently ruined. Sometimes the failure is dramatic, a transformer that erupts in fire or bursts its tank. More often, it is quiet and insidious internal damage that may not announce itself immediately, but leaves the machine fatally weakened, failing days or weeks later, or simply unfit to ever be trusted with the grid's full load again. There is a defense against all of this, and it is worth knowing about, because it is the difference between a future where we ride out the great storm and one where we do not. Engineers can install devices that block the geomagnetically induced current from reaching the transformer in the first place. capacitors and resistors placed in the connection to the ground that stop the slow direct current while letting the normal alternating current flow freely. The technology to harden the grid largely exists. It is understood. The problem is that hardening a continent-spanning grid is expensive and slow. It requires utilities and regulators and governments to spend large amounts of money against a threat that has not yet materialized in their lifetimes. That kind of investment against an invisible, infrequent danger is exactly the kind of thing human institutions are worst at prioritizing. The hardening proceeds in patches here and there, far from complete, while the grid grows ever larger and more interconnected. We know how to protect ourselves. We have mostly not done it. This is the heart of the entire threat. I need you to understand why a destroyed transformer is so much worse than a blackout, because it is the difference between an inconvenience and a catastrophe. When the grid trips offline to protect itself, that is recoverable. Operators reroute power, bring plants back online, and the lights come back, sometimes within hours. A trip is the system doing its job. A destroyed extra-high-voltage transformer is a different kind of problem entirely, because of one brutal fact about how these machines are made. They are not sitting on a shelf. The largest transformers are not mass-produced. Each one is, to a significant degree, custom-built for the specific spot in the grid where it lives, engineered to its exact voltage and capacity. Building one is a major industrial undertaking that can take many months, and in some cases, more than a year from order to delivery. A great deal of the world's capacity to manufacture them sits in a handful of specialized factories, often on the other side of an ocean from where they are needed. They are so large and so heavy that moving even one of them requires special rail cars or heavy haul trucks and careful planning. Critically, no country keeps a vast warehouse of spares standing by. There are some reserves, some sharing arrangements, but nothing remotely close to what you would need if a storm destroyed not one transformer, but dozens or hundreds across a continent all at the same moment. Do you see the trap? In an ordinary disaster, a hurricane, an earthquake, the damage is regional, and the rest of the country surges in to help. Crews drive in from neighboring states. Equipment is trucked in from unaffected regions. A geomagnetic superstorm does not respect regions. The induced currents flow into long lines across an entire continent simultaneously. If the storm is large enough, it could saturate and destroy the great transformers in many places at once, and there would be no unaffected region to send spares from, and no warehouse to pull them out of, and no way to build the replacements in anything less than the better part of a year. The blackout would not be a thing that ends. It would be a thing you wait out in the dark for a season or more. There is a subtlety here that makes some regions far more vulnerable than others, and it is worth understanding because it determines who gets hit hardest. The strength of the current induced in the ground depends not only on the storm, but on what the ground itself is made of. Where the rock beneath the surface conducts electricity well, the induced currents can flow through the earth itself, and less of that current is forced up into the power lines. Where the bedrock is ancient, hard, and a poor conductor, the kind of old crystalline rock that underlies large parts of North America and Scandinavia, the ground refuses to carry the current, and so it is forced to find another path. The most inviting path is the long, well-grounded transmission line overhead. This is part of why the great northern grids, sitting on ancient shield rock and running long lines to bring power down from remote generation, are among the most exposed in the world. The geology of where you live, the rock you never think about beneath your feet, helps decide how hard the storm hits your lights. It is one more variable in a hazard already full of them. The worst-case map of a great storm is not uniform. Some regions sit on natural protection, and some sit on the opposite, and the lines that bring power to tens of millions of people often run straight across the worst of it. It is not only the power grid that turns into an antenna during one of these storms. Any long conductor does. The pipelines that carry natural gas and oil across the continent develop induced currents that accelerate corrosion and confuse the systems that monitor them. The signaling systems on railways can be disrupted. Undersea communication cables, the literal backbone of the global internet, carry induced currents during the strongest storms. The Earth, draped in the metal nervous system of an industrial civilization, becomes, during a great storm, a single vast circuit, energized from above by a changing magnetic field. And every wire we have ever strung becomes part of it. Tomorrow, this entire mechanism switches on. The induced currents will flow. The transformers will see a little extra heat, a little extra reactive demand, and the operators will manage it because a storm rated 7 is a trickle through this system, well within what it was hardened to survive after the lessons of the past. You will not lose power tomorrow because of the sun. The mechanism that keeps your lights on tomorrow is the exact same mechanism that, at a larger scale, takes them away. The only difference is the size of the flood. To understand how big that flood can get, we have to go back to a September night in 1859, when the sun did something that has never been equaled in the age of human record-keeping. The only reason it did not end the world is that the world back then had almost nothing for it to break. On the morning of the 1st of September, 1859, an English astronomer named Richard Carrington was doing what he did most clear mornings. He was at his telescope, projecting an image of the sun onto a screen, carefully sketching the sunspots crawling across its face. He had been tracking an unusually large and complex group of spots for days. As he watched and drew, something happened that no one had ever recorded before. Two brilliant points of white light erupted within the dark sunspot group, blindingly bright. So intense that Carrington at first thought a beam of sunlight had broken through somewhere in his equipment. It had not. He was watching, for the first time in human history, a solar flare with his own eyes. A flare so powerful it was visible in plain white light against the already blinding surface of the sun. Carrington noted the time. He did not know what he was looking at. Not really. No one did. The idea that the sun could reach across space and touch the Earth was barely a hypothesis. The Earth was about to be touched harder than it has been touched in all the centuries since. What makes the event that bears Carrington's name so staggering is not just the flare. It is the cloud that came with it, and how fast that cloud arrived. A typical coronal mass ejection takes 2 to 4 days to cross the distance from the sun to the Earth. The one launched that morning in 1859 made the crossing in roughly 17.5 hours. Think about what that speed implies. To cover that distance that fast, the cloud had to be moving with a violence that beggars description, plowing through the solar wind ahead of it, clearing a path, arriving with its energy almost undiminished. It is the fastest major Earth-directed cloud in the entire record. When it hit, the magnetic field of the Earth convulsed in a way that the instruments of the time, the simple magnetometers scattered around the world, swung clean off their scales. Then the wires began to do impossible things. The telegraph was the great technological wonder of 1859, the first time in history that information could move faster than a horse. A web of copper wire strung across continents. On the night the Carrington storm struck, the telegraph network became possessed. Operators reported sparks leaping from their equipment, arcs of electricity jumping to their hands and faces. Telegraph paper caught fire from the current surging through the lines. Some operators disconnected their batteries entirely because the aurora-induced current flowing through the wires was so strong that they could send messages on that alone. The Earth itself, powering the telegraph through the storm. The system had been energized by the sky. There is a detail in those telegraph accounts that I find almost unbelievable, and yet it is well documented. Two operators on a line between two cities found that the storm was wreaking such havoc with their equipment that they disconnected their batteries entirely. The power source the telegraph normally depended on, expecting to give up for the night. Then they discovered they could keep sending messages anyway, the line carrying their signals on the current induced by the storm alone. The aurora was running the telegraph. The Earth's own magnetic convulsion had become the power supply. For a few hours, the sky itself was the battery. It is a beautiful and terrifying image, and it is the cleanest possible demonstration of the principle at the heart of this whole video on the cosmic forecast, that a great storm pours real, usable, and ultimately destructive electric current into the long wires we string across the land. Above all of it, the auroras. Normally, the northern lights are a polar phenomenon, confined to the high latitudes near the magnetic poles. On the nights of the Carrington storm, they came south. Far south, they were seen in the Caribbean. They were reported near the equator. People in the lower United States woke in the middle of the night thinking dawn had come early. The sky so bright with red and green light that they could read newspapers by it. Miners in the Rocky Mountains got up and started cooking breakfast, convinced morning had arrived, when it was 1 in the morning. Birds began to sing, fooled by the false dawn. The whole sky across most of the planet was on fire with light. There is something worth sitting with in those accounts, beyond the spectacle, because they capture the sheer disorientation of people who had no framework to understand what they were seeing. They did not know about coronal mass ejections or geomagnetically induced currents. They did not know the sun had hurled a piece of itself at the earth. They only knew that the sky had turned the color of blood and fire in the middle of the night, that their telegraph machines had come alive with sparks, that something vast and inexplicable was happening above them. Some were awed, some were frightened. Some, in an age more given to such interpretations, took it for an omen. What none of them could grasp was the mechanism, because the science did not yet exist. We are in the opposite position. We understand exactly what causes it, exactly how it works, exactly what it could do to us. We have the framework they lacked. The strange thing, the almost darkly comic thing, is that having the full understanding has not made us safe. Because understanding a threat and preparing for it are two entirely different acts, and we have done a great deal of the first and not nearly enough of the second. Here is the thought experiment that should chill you, and it is the entire reason this event matters so much. In 1859, what did that storm have to destroy? The telegraph. A few thousand miles of wire and some batteries. That was the sum total of the electrical infrastructure of human civilization. There was no power grid. There were no satellites. There were no computers, no electric pumps moving the water, no refrigeration, no electronic finance, no internet, nothing. The most advanced technology, the most violent solar storm in recorded history could find to attack was the telegraph, and it set the paper on fire and moved on. Humanity barely noticed because humanity barely had anything to lose. We are not 1859. We are the opposite of 1859. We have spent the intervening century and a half building a civilization made of nothing but the things that storm attacks. We took the one vulnerability that storm exposed, the way it pours current into long wires, and we wrapped the entire planet in long wires. And then we plugged our food, our water, our money, our communication, our medicine, and our heat into them. If the Carrington event happened in 1859 and barely registered, and the same event happening now could cost trillions and take years to recover from, then the storm did not get more dangerous. We did. We built the target. There is a piece of physical evidence for just how extreme that storm was that I find genuinely haunting, because it is written into the planet itself. When the Earth is bombarded by the energetic particles of a great solar storm, chemical reactions high in the atmosphere produce certain compounds, including nitrates, that eventually settle out and get locked into the ice at the poles, layer by layer, year by year. Scientists can drill cores out of that ice and read the layers like tree rings, looking back across centuries and millennia for the chemical fingerprints of past solar storms. The work of reading those records, combined with the radioactive fingerprints that cosmic bombardment leaves in tree rings, has let researchers look for other Carrington-scale events in the deep past. What they find is sobering. There appear to have been events even larger than 1859 in the historical and prehistoric record. Storms so large that if one struck today, the word catastrophe would not begin to cover it. The sun is capable of more than it showed us in 1859. Carrington is not the ceiling. It is merely the largest one we happen to have instruments, however crude, to witness. The question that hangs over all of this is simple and unanswerable in a comforting way. How often does the sun do what it did in 1859? The honest answer is that we do not know precisely, because our detailed records are short, but the best estimates cluster around something like once or twice per century. Once or twice per century. The last confirmed one was over 160 years ago. Run that math however you like, but there is no version of it where we are safely far from the next one. We are squarely inside the window. We have been inside it for a while. The storm that lit telegraph paper on fire in a world that ran on horses would land, this time, on a world that cannot function for a single day without the exact systems it destroys. That is the benchmark. Now let me show you the only time in the modern era we got a real, undeniable taste of it. The night an entire province went dark in 90 seconds. It was just after 2:30 in the morning on the 13th of March, 1989. Across the Canadian province of Quebec, more than 6 million people were asleep in the deep cold of a Canadian March, their homes heated in many cases by electricity. The power was flowing, as it always did, from the great hydroelectric dams in the north down, a long spine of transmission lines to the cities in the south. Then, in the span of about 90 seconds, all of it collapsed. A geomagnetic storm had been building for hours, the product of a large solar eruption days earlier. The induced currents had been creeping into the long transmission lines that run down from the northern dams. And those lines are especially exposed because they run for great distances across a kind of ancient rock that does not conduct electricity well, which actually forces more of the induced current up into the grid itself. The currents pushed the system's equipment toward saturation. Voltage began to swing, and the protective devices that guard the grid started to sense that something was deeply wrong. One piece of equipment tripped. That shifted the load onto others, which pushed them past their limits, and they tripped too. In a cascade that took about a minute and a half from start to finish, the entire Hydro-Quebec grid, a system carrying around 21,000 megawatts, fell over. 21,000 megawatts is the output of a major power system, enough to run a province. It was gone in 90 seconds. In the dark, in the cold, 6 million people lost power. Heating systems died, the Montreal subway stopped, the airport went dark. It stayed down for about 9 hours while crews scrambled to understand what had happened and bring the system back, piece by careful piece. 90 seconds is the detail I cannot get past, and I want you to understand why it is so important. The collapse was not a slow degradation that operators watched coming and tried to fight. It was a cascade, and a cascade moves at the speed of electricity, which is to say almost instantly. It began when the geomagnetically induced currents caused equipment in the system to behave erratically, and a key piece of voltage-regulating equipment tripped offline to protect itself. The moment it did, the load it had been carrying shifted onto the rest of the system, which was already stressed, and that pushed other equipment past its limits, which tripped in turn, shifting still more load onto a shrinking number of remaining components, each one failing faster than the last. It is the same runaway logic as a row of dominoes, except the dominoes are spread across an entire province, and the whole row falls in less time than it takes to read this sentence aloud. By the time a human operator could even register that the first piece had failed, the entire grid was already down. There was no fighting it. There was no human in the loop fast enough to matter. That is what a geomagnetic storm can do to a power system. It did it in 1989 to a grid that was, by the standards we are discussing, only moderately stressed. 9 hours is survivable. People bundled up, waited it out, and the grid came back. As disasters go, the Quebec blackout was a hard night, not an apocalypse. That is exactly why it is so important to understand, because of two facts that, when you put them together, should make the hair on your neck stand up. The first fact is the mechanism. What happened over Quebec that night was not a freak accident or a piece of equipment that happened to fail. It was the textbook scenario. It was geomagnetically induced currents doing precisely what the physics says they do: saturating transformers, destabilizing voltage, triggering a protective cascade, collapsing a grid. It was the trickle becoming, for one province, a flood. It did not stop at Quebec. That same storm reached down into the northeastern United States, and at a power station in New Jersey, a large transformer was pushed so hard by the induced currents that it was permanently damaged. Not tripped, destroyed. A multi-million-dollar machine cooked from the inside by a storm on the sun. That is the destruction I described earlier, made real in 1989 on this side of the world. That New Jersey transformer is worth lingering on, because it is the single clearest piece of evidence that the destruction scenario is not theoretical. It was a large generator step-up transformer at a nuclear plant, one of those custom-built machines that take the better part of a year to replace. The geomagnetically induced currents from the storm drove it into exactly the saturation and overheating I described. And the internal damage was severe enough that the machine was effectively finished. The storm on the sun reached across 93 million miles and ruined a specific, identifiable, multi-million-dollar piece of American infrastructure. It happened. It is in the record. It happened during a storm that, again, was nowhere near the worst the sun can do. If a moderate storm can reach down and kill one named transformer in New Jersey, the worst case is not a question of whether transformers die. It is only a question of how many, and where, and whether the number overwhelms our ability to replace them. The 1989 event answered the first question for us decades ago with a single dead machine. We have simply chosen not to act on the answer. Here is the second fact, the one that turns the story from history into warning. By the standard of what the sun is truly capable of, the storm of March 1989 was not a great storm. It was a strong one, yes, serious, but nowhere near the scale of 1859. It was perhaps a third, maybe less, of the intensity of a true Carrington-class event. That merely strong storm, that fraction of the worst case, collapsed an entire province's power grid in 90 seconds and destroyed a transformer hundreds of miles away. The 1989 storm did more than just Quebec and New Jersey, which is part of why it is such a good teacher. Across the northeastern United States and into the grids of other regions, operators spent that night fighting to keep their own systems from following Quebec into the dark. Watching their voltages swing and their equipment strain, some of them coming closer to collapse than the public ever knew. Power systems well to the south of Canada logged the stress. The auroras, as they always do during a great storm, came south with it. The northern lights seen that night far below their usual range, reported in parts of the world that rarely glimpsed them, down toward the latitudes of the Caribbean. Once again, a fainter echo of what 1859 had done. This was not a narrowly Canadian event that happened to take down one unlucky grid. It was a continental stress test, and Quebec was simply the place where the system broke first and hardest. Everyone else passed the test that night by a narrower margin than they would have liked, and the storm that administered it was, to say it one more time because it matters so much, nowhere near the worst the sun can throw. Sit with the arithmetic of that. If a storm a fraction of the size of the worst case can drop a regional grid in a minute and a half and kill a transformer in another country, what does the full Carrington scale event do? It does not do it to one province. It does it to a continent. The induced currents do not flow into one spine of northern transmission lines. They flow into every long line across an entire landmass at once. The cascade does not trip one grid. It races across interconnected grids that span whole nations, because our power systems are wired together precisely so that power can flow where it is needed. Which means that when one region fails violently enough, it can drag its neighbors down with it. The transformers that die are not one in New Jersey. They are potentially dozens, hundreds, scattered across the map, each one a custom-built machine that takes the better part of a year to replace, with no warehouse of spares to draw from. Here is the cruel irony buried in the way we have built our grids. We connected them together on purpose, wired region to region and nation to nation, precisely to make them more reliable. The logic is sound for ordinary failures. If one power plant goes down, its neighbors can pick up the slack, power flowing in from elsewhere to cover the gap, and the lights stay on. Interconnection is a brilliant defense against the everyday breakdown. Interconnection is exactly the wrong design against a continent-wide threat that hits everything at once. The same wires that let a healthy region rescue a sick one also let a violently failing region drag a healthy one down with it. During a great geomagnetic storm, there is no healthy region to do the rescuing, because the induced currents are flowing into every long line across the entire landmass simultaneously. The interconnection that protects us against small local failures becomes the very pathway by which a large global failure propagates. We built a system optimized against the disaster that happens often and accidentally maximized our vulnerability to the disaster that happens rarely but catastrophically. The Quebec blackout lasted 9 hours because the grid was not destroyed, only knocked down, and the machines needed to rebuild it still existed and still worked. Now imagine the version where the machines themselves are gone, where the transformers that would let you rebuild the grid are the very things the storm destroyed. That blackout does not last 9 hours. That is the version measured in months. It is the version where the lights staying off is only the beginning of the problem. Because everything else we depend on is downstream of electricity, and we forget that until it is gone. The water that comes out of your tap is pushed there by electric pumps. The fuel at the gas station is pumped from underground tanks by electric pumps, which means that, in a long blackout, even the cars and generators that could help you are stranded next to fuel they cannot reach. The food in the stores and the medicine in the pharmacies sit in refrigeration that runs on power. The money in your bank is numbers in a computer that needs electricity and a network. Hospitals run on backup generators that run on fuel that runs out. A modern city is a machine for keeping millions of people alive in a small space, and that machine runs on electricity. A great geomagnetic storm is the one natural disaster that can switch the machine off across an entire continent at the same moment, and then destroy the parts you would need to switch it back on. Quebec in 1989 was the small, survivable rehearsal. 9 hours, a hard night. The lights came back. It was the G2 of grid collapses. We should be grateful we got that rehearsal, because it taught the engineers real lessons, and the grid is more hardened today because of it. The rehearsal is not the performance. The closest the modern world has actually come to the performance, the real one, the Carrington scale event aimed at us in the satellite age. Happened not in the distant past, but well within living memory, and we missed it by about 1 week. Let me tell you about the storm of 2012, the one that should have been the end of the conversation about whether this can really happen, because it already did. On the 23rd of July, 2012, the Sun launched one of the most powerful coronal mass ejections ever measured by human instruments. It tore off the surface and rocketed out into space at a speed that, by some measures, rivaled or exceeded the 1859 event. It was a true monster, a Carrington-class cloud. The kind of thing scientists had spent decades wondering whether they would ever get to measure directly. They did get to measure it directly, in exquisite detail. Because the cloud happened to roll straight over one of the spacecraft, we had stationed out in the solar system to watch exactly this kind of thing. Then it sailed off into empty space, and the Earth went about its day, and almost no one outside the small community of space, whether scientists ever knew it happened. The reason we survived the most powerful solar storm of the modern era is almost insultingly simple. It missed. The region of the Sun that fired it was not pointing at us when it fired. Because the Sun rotates roughly once every 27 days as seen from Earth, each spot on its surface spends only part of its time facing our way. The monster cloud of July 2012 erupted from a part of the Sun that had been aimed directly at Earth about a week earlier. 1 week. If that same eruption had happened 7 days sooner, while that region was squarely facing us, the cloud would not have flown off into empty space. It would have hit the Earth dead on with its full violence intact. We know roughly what would have happened, because the spacecraft that got hit measured the cloud completely. Scientists ran the numbers, asking what the storm would have done had it struck the Earth, and the answer they came back with is sobering. The intensity, by the standard measure of how hard a storm pushes the Earth's magnetic field, would have reached a level comparable to the Carrington event itself, and roughly twice the severity of the storm that took down Quebec in 1989. A direct hit by the July 2012 cloud would not have been a regional 9-hour inconvenience. It would have been the continental, multi-month, transformer-destroying catastrophe we have been circling this entire video on the cosmic forecast. The only thing standing between us and that outcome was the calendar, a timing of about 1 week in the Sun's rotation. The fact that we measured it so well is its own kind of gift and warning, because the cloud rolled directly over a spacecraft positioned out in the inner solar system. Instruments built to study the Sun got a complete, detailed reading of a true Carrington-class event from the inside, something they had never had before. They could see the speed, the density, the magnetic field strength, the orientation, everything. It was, in a strange way, the best characterized monster storm in history. The reason we can say with confidence what it would have done is that we did not have to guess about the cloud. We had the numbers. The numbers said that this thing, had it arrived 7 days earlier, would have struck Earth with a southward-leaning field and the full intensity intact. Exactly the worst-case combination. The loaded gun, fired with the safety off, missing only because the barrel happened to be pointed a few degrees away from us in the moment it went off. One of the scientists who studied it put it in a way I have never been able to forget. He said that we passed through the crosshairs and we were not hit, and most people had no idea we had even been in the line of fire. We dodged the bullet by being in the wrong place at the right time, by sheer orbital luck, and we did not even feel the wind of it passing. That is how close it was. That is how recent it was. This is not a hypothetical dredged up from the 19th century. This is a near miss from a year many of you watching can remember clearly. An event that says, in the plainest possible terms, the big one is not a question of if. The big one is a thing that already happened. It's simply, mercifully missed. I want to dwell on that reframing for a moment, because it changes the whole emotional shape of this threat. When we talk about most catastrophic risks, we are talking about probabilities, about models and projections of something that has not occurred. And it is easy for the mind to file those away as abstractions, as the kind of thing that happens to other generations. The Carrington-scale solar storm is not in that category anymore. We do not have to imagine whether the sun can produce one in our era, because it did in 2012, and we have the measurements to prove it. The only reason we are not still digging out from it is the geometry of where that region happened to be pointing on the day it erupted. Strip away the comforting fact that it missed, and what you are left with is this. In the modern, fully electrified, satellite-dependent era, the sun has already fired a world-ending scale solar storm directly across Earth's orbital path. The gun has been fired. We have seen the muzzle flash and measured the bullet. We just happen not to be standing in front of it that particular week. The sun will fire again on its own schedule, indifferent to whether we are ready, and the next time the geometry might not be so kind. This lets us answer the question of what a direct hit would actually cost, because serious people have done the work of estimating it. A major report from the National Academy of Sciences, the body that advises the United States government on exactly these kinds of questions, looked hard at what a Carrington-scale storm would do to a modern, electrified society. The number they arrived at for the economic impact in the first year alone was somewhere between 1 and 2 trillion. Not billion, trillion. The recovery time for the worst affected regions, they estimated, would run not weeks, not months, but somewhere in the range of 4 to 10 years. I want to make sure that recovery number lands, because it is the single most important and least intuitive part of this whole story. When we hear about a disaster, we picture damage and then repair. The hurricane passes, the crews come in, and over weeks and months, things are rebuilt. Our entire instinct about catastrophe is that it is a thing that happens and then is fixed. The geomagnetic superstorm breaks that instinct because of the transformer bottleneck I described earlier. The recovery is not slow because there is so much to repair. The recovery is slow because the specific machines you need to repair it are the machines that were destroyed, and they take the better part of a year each to build, and there is no stockpile. And the factories that make them are few, and now, suddenly, the entire world is ordering them at once. 4 to 10 years is not how long it takes to clean up. 4 to 10 years is how long it takes to manufacture your way back to a functioning grid while a continent waits, in conditions we have not collectively experienced since before electricity. I want to head off the natural objection, the one that says surely we would just rush to build more transformers. Surely a crisis like that would mobilize industry the way a war does. The trouble is that you cannot mobilize your way out of a physics and engineering bottleneck on a short timeline. Building an extra high-voltage transformer is not like building a car on an assembly line that you can simply run faster. It requires specialized facilities, vast quantities of specific high-grade electrical steel, copper, precision manufacturing, and a testing process that cannot be safely rushed. Because a transformer that fails in service is worse than no transformer at all. The number of factories in the world capable of making the largest ones is small. In a normal year, they produce enough to meet normal replacement demand, and not much more. Imagine the entire developed world placing emergency orders simultaneously, all of them needing the same scarce steel, and the same scarce manufacturing slots at the same moment. With global shipping itself degraded, because shipping runs on the very systems the storm took down. The queue does not clear in months. It clears over years, and the regions at the back of the queue wait the longest. There is no amount of money that makes electrical steel and precision winding happen faster than physics allows. That is why the recovery estimate is 4 to 10 years, and not 4 to 10 weeks. The bottleneck is real, and it is not a failure of will. It is a failure of foresight. The foresight to have built the spares and the surge capacity before we needed them. Think about what 4 to 10 years without reliable power across a large region actually means for the people living through it. It is not a long camping trip. It is the collapse of the systems that allow tens of millions of people to live concentrated in cities, water systems that cannot pump, sanitation that cannot run, food distribution that depends on refrigeration and electric logistics grinding down, medicine that cannot be kept cold, hospitals burning through fuel for generators that eventually runs dry, because the pumps that move the fuel also need power. Every dependency I listed for Quebec's 9 hours, stretched not over a night but over years. The estimates of what that does to a society in terms of human cost are grim enough that I am not going to dwell on them, but you can do the arithmetic yourself. The modern world is a machine for keeping enormous numbers of people alive in close quarters. That machine runs on the grid. The grid is the thing the storm takes away and makes hardest to give back. I want to be careful and honest here, because this is exactly the kind of place where it would be easy to tip over into doom for its own sake, and that is not what this is. The point of laying out the worst case in this much detail is not to frighten you into despair. It is the opposite. It is that this is, almost uniquely among the great natural threats, a disaster we can see coming in principle and prepare for in practice. We cannot stop an earthquake. We cannot talk a hurricane out of forming. The geomagnetic superstorm is a threat we understand mechanically, down to the physics of how the current flows and which machines fail and why. We know which devices would block the currents. We know we could build reserves of spare transformers. We know we could write the operating procedures that let grid operators shed load and protect equipment in the crucial minutes, when the warning comes in from that spacecraft, 1,000,000 miles upstream. The recovery being measured in years is not a law of nature. It is a consequence of choices we have not yet made. The terrifying implication comes with the strange thread of hope running through it. The hope that lies in the word preventable. The storm is coming. The catastrophe is optional. The only question is whether we treat the small storms, the ones like tomorrow's, as the free warnings they are, or whether we keep filing them away as light shows and forgetting them by the weekend. That is the worst case, fully assembled. A Carrington-scale cloud, which the sun produces once or twice a century, and which we know it can produce because it nearly produced one for us in 2012. Arriving with its magnetic field pointed the wrong way for us, throwing the doors of the magnetosphere wide open, flooding a continent's worth of long wires with induced current, saturating and destroying the great transformers all at once, and dropping the grid into a darkness that the destroyed machines themselves make it take years to lift. That is the terrifying implication of the pretty lights you may see tomorrow. The same sun, the same physics, the same kind of clouds scaled up and aimed right on a calendar we do not control. But the storm is only half of why we should be afraid. The other half is what we have done to ourselves. We did not just fail to protect against this. We built on purpose the most exposed civilization that has ever existed, and we are getting more exposed every year. Let me show you exactly how naked we have made ourselves. We have spent this whole video on the cosmic forecast down on the ground, talking about transformers and transmission lines, and that is where the most catastrophic damage would happen. The great storm reaches higher than the ground. It reaches all the way up to the machines we have placed in orbit. In the span of a single human lifetime, we have come to depend on those machines for things our grandparents would not have believed. And they sit in the exact environment that a solar storm turns hostile. Start with what the storm does to the air itself, way up high. When a geomagnetic storm pours energy into the upper atmosphere, it heats it. Heated air expands. The thin wisp of atmosphere that still exists at the altitudes where many satellites fly, a few hundred miles up, puffs up and grows denser during a storm. A satellite flying through suddenly thicker air feels more drag, more resistance, like a swimmer who finds the water has turned to syrup. That drag pulls at the satellite, robs it of speed, and drags its orbit lower. We have already watched this happen at the small scale. During a geomagnetic storm just a few years ago, far from a worst-case event, a batch of newly launched communication satellites flew straight into atmosphere that a storm had puffed up. And the extra drag dragged dozens of them down out of orbit before they could climb to their operational altitude, and they burned up. Dozens of satellites lost to a storm that did not even rate as a great one. Scale that to the worst case, and to the thousands upon thousands of satellites we now have circling the planet, and you begin to see the exposure. Then there is the thing those high-energy electrons do, the ones I told you to remember from earlier in this video, the ones that spiked to 1,284 units on the 6th of June. When the flux of those fast electrons climbs, they do not just bounce off a satellite, they penetrate it. They burrow into the insulating materials inside the spacecraft and build up a static charge deep in its guts. When that buried charge finally lets go, it discharges in a tiny internal lightning bolt that can fry the electronics from the inside. Engineers call it internal charging, and it is one of the leading ways that space weather kills satellites. The number we logged this week, that 1,284, was high enough to trigger an automatic alert. In a worst-case storm, that environment becomes far more severe, and the satellites flying through it are gambling their electronics against it. Consider how much more there is up there to gamble now than there was even a decade ago. We are in the middle of the largest expansion of objects in orbit in the history of spaceflight. Where once there were hundreds of active satellites, there are now many thousands, with plans for tens of thousands more. Great constellations of small spacecraft strung across low orbit to beam internet to the entire planet. Each one is a node in a system that more and more of the world relies on. Each one is flying through the same environment that a great storm turns into a shooting gallery of drag and charging. The more we put up there, the more we have exposed. The small spacecraft that make up the new megaconstellations are, by design, cheap and light and not heavily shielded, which makes them economical to launch by the thousand, and also makes them more vulnerable, not less, to the conditions a storm creates. We have not just built a fragile system on the ground. We are building a second fragile system in the sky and wiring the two of them together and pointing both of them at the sun. The deepest exposure, the one almost no one thinks about, is timing. When you think of the satellite navigation systems, GPS and its cousins, you think of the little blue dot on your map. A great storm does scramble that. The same disturbed upper atmosphere that drags down satellites also distorts the path of the navigation signals passing through it, smearing the timing, degrading the accuracy, sometimes knocking it out entirely across the sunlit half of the planet. So yes, your map stops working, but that is the least of it because those navigation satellites are not really at their core location machines. They are clocks. astonishingly precise clocks in orbit. The entire system works by broadcasting the time so accurately that your receiver can figure out where it is from the tiny differences in when the signals arrive. We have quietly wired those orbital clocks into the foundations of modern life in ways that have nothing to do with navigation. The financial system uses that precise timing to stamp transactions, to keep the markets synchronized down to fractions of a second. The telecommunications networks, the cell towers, use it to keep their signals coordinated. Power grids themselves use it to keep their many parts in step: logistics, shipping, data centers, all leaning on a timing signal that comes down from satellites. In an environment a great storm turns toxic. When the storm degrades the navigation system, it is not just lost travelers. It is a tremor that runs through finance and communication and the grid itself, through systems most people have no idea are even connected to the sun. This hidden dependence on satellite timing is, to me, one of the most quietly alarming facts about how we have built the modern world, because it grew up invisibly, without anyone deciding it should be a single point of failure. When those navigation satellites were first launched, they were for finding your position. The timing signal they broadcast turned out to be so precise and so free that engineers in every industry quietly built it into their systems as the cheap universal clock. The stock exchanges use it to timestamp trades to the microsecond, which matters enormously when fortunes are made and lost in the gap between one microsecond and the next, and when the law requires those timestamps to be accurate. The cell networks use it to keep their towers handing your call from one to the next without dropping it. Data centers use it to keep their servers agreeing on what time it is. Which sounds trivial until you realize that databases spread across the world can corrupt themselves if they disagree about the order in which things happened. Even parts of the power grid use it to keep distant pieces of the system synchronized in phase. We took a clock in the sky and wove it into the foundations of finance, communication, computing, and energy all at once, all leaning on the same handful of satellites in the same hostile environment. And almost no one outside the engineering of those systems knows the dependence exists. A great storm that degrades that timing signal does not announce itself as a satellite problem. It announces itself as 1,000 seemingly unrelated glitches across 1,000 systems, all tracing back, if anyone had time to trace them, to the same disturbed sky. On top of all of that, the most immediate effect of all, the flare's radiation reaches the Earth at the speed of light and slams the upper atmosphere on the daylight side. And the high-frequency radio waves that bounce off that part of the atmosphere to travel around the curve of the Earth suddenly cannot. High-frequency radio blacks out across the entire sunlit half of the planet during a strong flare. High-frequency radio is not some quaint relic. It is how aircraft crossing the great oceans, out of range of any ground tower, stay in contact. It is the backbone of emergency communication when everything else fails. During the worst of one of these events, the very communication channel you would fall back on in a crisis is the one the crisis takes away first. Now let me assemble the cascade of an ordinary day in a long blackout, because this is the part that I think people genuinely fail to imagine, since we have never had to. We picture a power outage as the lights going off and the refrigerator going quiet, an inconvenience that ends when the power company fixes the line. Strip the power away from a modern city for not hours but weeks, and the failures stack on top of one another in an order most people never think about. The water stops because the pumps that push it up into the towers and through the pipes run on electricity. Within a day or two, the taps go dry and the toilets stop flushing. The fuel becomes unreachable because the pumps at the gas station are electric, which means the generators people bought for exactly this emergency cannot be refueled once their first tank runs out. And the trucks that would bring more fuel cannot be filled either. The food in every store spoils as the refrigeration dies, and no new food arrives because the distribution system that restocks the shelves runs on electric logistics, refrigerated trucks, and fuel that cannot be pumped. The money in the bank becomes inaccessible because it was never paper. It was numbers in a computer that needs power and a network. The pharmacies cannot keep insulin cold. The hospitals run their generators until the fuel runs out, and then they are simply dark buildings full of people who depended on machines. Communication degrades as cell towers exhaust their backup batteries. All of this is happening, not in one neighborhood that can be helped by the next, but across a region too large for any outside help to reach, for a span of time too long for anyone to have stockpiled against. That is the difference between a blackout and a collapse. A blackout is the lights going off. A collapse is every system that keeps millions of people alive failing in sequence, with no quick way to turn any of them back on. The only thing standing between those two outcomes is the size of the storm and the luck of its timing. Assemble the whole picture of what we have built. We took a hazard whose one great weakness, demonstrated all the way back in 1859, was that it pours destructive currents into long wires and disturbs the space around our planet. Then, knowing this, we strung the longest wires in history across every continent. We filled the sky above us with thousands of satellites. And we made the timing signals from those satellites the invisible heartbeat of our money, our communication, and our power. We did not just fail to harden ourselves against the storm. We engineered ourselves, year by year, decade by decade, into the most perfectly vulnerable configuration a solar storm could ever hope to find. Every new satellite launched, every new system that leans on GPS timing, every mile of grid wired more tightly to its neighbors, makes us a little more efficient on the good days, and a little more exposed on the day the big one comes. We are more dependent on these systems this year than we were last year, and we will be more dependent next year than we are now. The target is not just built. It is still growing, and the growth runs in exactly the wrong direction for our safety, because every trend in modern technology deepens the dependence rather than reducing it. We are electrifying everything we can, moving transportation onto the grid, moving heating onto the grid, building data centers that consume the power of small cities. All of it admirable for other reasons, and all of it concentrating more of human life into the single system the storm attacks. We are pushing more of our communication and our commerce into networks that assume constant power and constant connectivity. We are launching satellites faster than at any point in history. Each of these is progress, and each of them is also a thicker thread tying our survival to the things a great storm severs. A century ago, the Carrington event found a world with almost nothing to break. 50 years ago, it would have found a world with a vulnerable grid but no satellite dependence and far simpler systems. Today, it finds the most interconnected, most electrified, most timing-dependent civilization that has ever existed. Tomorrow, in the literal sense, it finds one slightly more exposed than today. We are not standing still and waiting for the storm. We are walking toward it, building the target higher with every year that passes, mistaking our growing efficiency for growing security, when it is, in this one specific and crucial way, the precise opposite. That is the terrifying implication fully stated, not that tomorrow's storm is the end. Tomorrow's storm is nothing, a trickle, a light show. The terrifying implication is that tomorrow's storm is the small, harmless face of a force we know can wear a catastrophic one, that we know is coming on a time scale of a human life or less, that already nearly arrived in 2012, and that we have spent the entire modern era making ourselves more and more helpless against. We are exposed. That is the honest word for it. We are exposed, and we are getting more so. Before I bring this home, I owe you the other half of intellectual honesty, because there is a great deal of nonsense that circulates around solar storms. And part of respecting you is telling you clearly where the real danger ends and where the fantasy begins. If you spend any time online when a solar storm is in the news, and you almost certainly have, you will run into a parallel universe of claims about what these storms do. I want to walk through the big ones with you, not to mock anyone, because the underlying instinct is often a healthy one, but to separate cleanly what the science supports from what it does not. The real danger I have spent this video on the cosmic forecast describing is frightening enough on its own. It does not need to be inflated. Inflating it actually makes it easier for serious people to dismiss the genuine threat. The most common claim you will see is that geomagnetic storms trigger earthquakes and volcanic eruptions. The story goes that the sun energizes the earth, and that this energy shakes loose the faults and stirs up the volcanoes. The evidence offered is usually a cluster of eruptions or quakes happening around the same time as a storm. I understand why it is seductive, because the timing can look striking. Right now, as this storm approaches, there are notable volcanoes active around the world. There is a volcano in Alaska sitting on elevated alert level. The Great Shield volcano in Hawaii has been putting on a show. There are ongoing eruptions across Indonesia, Russia, and the Philippines. The pattern-matching part of the brain says, look, the sun is acting up and so is the earth. Surely they are connected. Here the physics is decisive, and I want to be precise about it, because precision is the whole point. The amount of energy a geomagnetic storm actually couples into the solid body of the Earth is real, but it is many orders of magnitude smaller than the energy involved in geology. The strain energy stored in a fault that is approaching the point of rupture, energy built up over decades and centuries of the slow grinding of tectonic plates, is colossal. The thermal and pressure energy driving a volcanic system, the heat of molten rock kilometers down, is colossal. The trickle of electromagnetic energy that a storm pushes into the ground is, by comparison, a whisper next to a thunderclap. It is not that the connection is small. It is that the connection is so small it cannot do the job it is being credited with. When scientists have gone looking carefully, statistically, for a real correlation between solar activity and earthquakes or eruptions, what they find comes back weak to nothing. The apparent clustering is what you get from the ordinary background drumbeat of a geologically active planet, which always has volcanoes erupting and faults slipping somewhere. Viewed through the lens of a storm that happens to have everyone paying attention at that moment. The volcanoes in Alaska and Hawaii and Indonesia are erupting because of their own internal clocks, the slow rhythms of magma and pressure, that have nothing whatsoever to do with what the sun did this week. The timing is coincidence. The physics does not support causation. I would be doing you a disservice to tell you otherwise. There is a deeper trap in this kind of reasoning that is worth naming directly, because it is a trap the human mind falls into constantly, not just with solar storms. It is the trap of seeing two dramatic things happen near each other in time, and assuming one caused the other. Our brains are pattern-finding machines, exquisitely tuned to spot connections, and that tuning served our ancestors well. It also means we see causation where there is only coincidence, especially when both events are vivid and frightening. The planet always has volcanoes erupting somewhere. On any given day, there are dozens of active volcanoes around the world, and earthquakes large and small are happening constantly. Because we live on a geologically restless planet, whose interior is still hot and churning. If you wait for a solar storm and then look around the world for an eruption or a quake, you will always find one. Not because the storm caused it, but because there is always one to find. The storm did not summon the volcano. The volcano was already erupting, and the storm just gave you a reason to look. This is the single most important habit of mind I can offer you on this topic, and on every topic this channel covers. The discipline to ask not just whether two things happen together, but whether there is a mechanism that could actually connect them, and whether the connection survives when you check it carefully against the data rather than against your gut. On the solar seismic question, it does not survive. The mechanism is too weak, and the careful checks come back empty. There is a more sophisticated cousin of this claim that points to faint electric signals measured at certain ground stations. Narrow bands of activity in the electric field that some researchers have proposed might serve as precursors to earthquakes. I want to be fair here, because this one is genuinely a topic of active research rather than pure fantasy. There are real scientists looking at whether the Earth gives off subtle electromagnetic warnings before it ruptures. And this is the crucial but, the predictive value of these signals is unestablished. An isolated, short-lived anomaly picked up at a single station is not a validated earthquake forecast. It is a curiosity that may or may not mean anything. The honest state of the science is that we cannot yet reliably predict earthquakes by any method, electromagnetic or otherwise. When you see someone point to a blip on a spectrogram and announce an earthquake is coming, the appropriate response is interest, not alarm. The research exists. The reliable prediction does not. Treating the one as the other is where it goes wrong. It is worth being precise about why this distinction matters so much, because it is easy to hear me debunking these claims and conclude that I am dismissing the whole field, and I am not. There is real, careful science being done on whether the Earth gives off detectable signals before a large earthquake, on changes in the electric and magnetic environment, in the behavior of the ground, in the gases that seep up from stressed rock. Some of it is genuinely promising as research. There is a vast gulf between an interesting research signal and a usable prediction, and that gulf is exactly where careful science lives, and where bad science pretends the gulf does not exist. A usable earthquake prediction would have to tell you where and when and how big, reliably enough that you could act on it without crying wolf so often that everyone stops listening. Nothing in the electromagnetic precursor research is anywhere near that bar yet, and honest researchers in the field are the first to say so. The failure mode is not in studying these signals. The failure mode is in taking a single anomalous reading from a single instrument and dressing it up as a forecast, which is not how the careful version of this science talks at all. So hold both things at once. The research is real and worth funding. The predictions you see announced online from a single blip are not science. They are pattern matching wearing the costume of science, and the difference between the two is the whole discipline. Then there is the claim that the authorities are hiding the true severity of the storm from us, downplaying the danger to prevent panic. Here, the reality is almost the exact opposite of the accusation. The forecasts are public. The watch I told you about at the start of this video is posted openly, free for anyone to read. The raw solar wind data, streaming back from the spacecraft upstream of Earth, is published in close to real time. Observatories all over the world in many different countries are watching the same sun and producing the same data, which makes coordinated suppression essentially impossible. The reason the forecasts come with uncertainty is not that someone is hiding the truth. It is that the truth genuinely cannot be known in advance. Because of that magnetic orientation we cannot measure until the cloud is nearly here. The difficulty is physics, not concealment. If anything, The people who study this are trying to get the public to pay more attention, not less. Think about how strange the suppression theory is when you actually examine it. For there to be a cover-up, you would need every space weather agency in every country to be in on it, because the United States is not the only nation watching the sun. There are observatories and forecasting centers across Europe, in Asia, run by different governments with different interests, often openly skeptical of one another. All of them watching the same sun and publishing the same numbers. You would need the operators of the spacecraft to falsify their public data streams, the same streams that thousands of independent scientists and even amateur space weather enthusiasts download and analyze every single day and would instantly notice being tampered with. You would need the universities, the journals, the international collaborations, all to keep the same secret forever, with nothing leaking. The machinery of a cover-up that large is simply not consistent with how science on this scale actually works, where the entire incentive structure rewards the researcher who finds the thing everyone else missed. The far more mundane and far more useful truth is that the data is right there, open to anyone, and the people who understand it best are not muffling the alarm. They are the ones ringing it, in reports and testimony and papers, mostly to a public and a set of institutions that have not yet decided to listen. Here is what I want to leave you with about all of this, because underneath the bad versions of these claims is a real and legitimate concern that deserves to be honored. The instinct that says this storm could really hurt us is correct. The instinct that says the threat is being underappreciated is correct. The instinct that says we are not as protected as we should be is correct. The grid genuinely is vulnerable to geomagnetically induced currents. The work of hardening it, of installing the devices that can block those currents from reaching the great transformers, of building up reserves of spares, of planning for the worst case, is genuinely incomplete. The danger is real. It is just that the real danger is the grid and the satellites, the wires and the orbital clocks, the prosaic, unglamorous infrastructure of modern life, not the volcanoes and not the earthquakes. The truth is less mystical than the fantasy, and far more frightening, because the truth is something we could actually do something about, and mostly have not. I want to spend the next stretch of this video on the cosmic forecast on the part of this story that is the hardest to tell, because it is not about the sun at all. It is about us. About the way human institutions handle a danger that is not yet on fire. Because if you want to understand why we are still vulnerable to a Carrington-class event 167 years after the last one, you have to understand the psychology of long-tail risk and the way it interacts with the timescales on which boards, executives, regulators, and elected officials actually make decisions. A geomagnetic superstorm is what risk analysts sometimes call a high-impact, low-probability event. The impact when it comes is civilizational. The probability in any given year is small. Each individual year, you can shrug it off and almost always be right. Each individual quarter, the question of whether to spend large amounts of money hardening transformers and stockpiling spares looks like a poor allocation of capital against a threat that did not materialize last quarter and probably will not next quarter. Every quarter you choose against it, you are correct in the short term. Eventually, on a timescale that no single quarterly report cares about, you are catastrophically wrong once. And the cost of being wrong that one time dwarfs everything you saved in all the prior years combined. This is the trap that long-tail risk always sets, and it does not just catch the power industry, it catches everyone. It is the reason pandemics tend to find us underprepared, the reason cities perched at the foot of historic volcanoes drift back to complacency between eruptions, the reason floodplains keep getting built on between 100-year floods. The human institutions we have built do not, on their own, naturally pay the cost today of avoiding the disaster of 40 years from now. They are not designed to. And the people working inside them are not stupid or malicious. They are operating inside a structure that rewards certain choices and punishes others. And the structure does not reward the engineer who quietly prevents a catastrophe that never comes. Sit with the asymmetry of that for a moment, because it is enormously important. If a grid engineer somewhere convinces their utility to spend $100 million hardening the most exposed transformers, installing the blocking devices, building the spare capacity, and writing the protective operating procedures, and then the great storm comes and the grid stays up because of that work, almost no one will ever know. The disaster that did not happen does not generate headlines. The engineer does not get a parade. The utility does not get rewarded by investors for the catastrophe its preparation averted, because investors only know to praise companies for outcomes they can see. The $100 million looks, in hindsight, like money spent on a problem that never materialized. If instead that same engineer fails to make the case, and the utility skips the investment, and the storm comes, and the grid falls, the engineer is not the one who pays the price. The price is paid by the public, in months without power, in food spoiling, in hospitals running on dwindling fuel, in the slow grinding loss of a way of life. The utility executives who decline the investment will, by then, mostly be retired or working elsewhere, and the decisions that mattered most will be untraceable in the rubble. The asymmetry of consequences runs in exactly the wrong direction. Heroism for prevention is invisible. The cost of skipping it lands on someone else, far in the future, when no one remembers who said no. It is into this asymmetry that the small storms keep arriving and being filed away as light shows. Tomorrow's storm, if it performs as forecast, will give us auroras and a brief stress on the grid and almost nothing else. It will be, in the local sense, a non-event. And the danger in non-events is that they teach a lesson that is not true. They teach us that the forecasters are crying wolf. They teach us that the storms come and the lights stay on, that the warning watches scroll past us harmlessly week after week, and that the people sounding the alarm must be either alarmist or wrong. The lesson is wrong because it confuses the storms we have lived through with the storm we have not. The fact that tomorrow's storm will not collapse the grid says nothing about the storm that will, when it comes. It is like watching small tremors in a region prone to great earthquakes and concluding from their harmlessness that the great earthquake will never come. The small tremors are not the warning that the great one is harmless. They are the warning that the same fault is loaded. There is a body of analysis on what it would actually cost to harden a continental grid against a Carrington-scale storm in a meaningful way, and the numbers are not small. They are also not nation bankrupting. The estimates run, depending on how aggressive the hardening, into the tens of billions of dollars spread over years. That is real money. It is also, when set against the trillion-dollar-plus impact of even a single direct hit, a bargain so steep it would be embarrassing if we were not also failing to take it. We are choosing to underinvest in a hedge against a disaster whose expected cost, when you multiply impact by probability over a span of decades, comfortably exceeds the cost of the hedge by a large factor. We are doing it not because the math is unclear, but because the political and institutional machinery that would have to act on the math is built to optimize for shorter horizons than the horizon on which the storm operates. One of the strangest features of this situation is how much of the hard scientific and engineering work is already done. We know what the storm is. We know how it couples into the grid. We know which devices block the induced currents. We know which transformers are most exposed. We know how the cascade propagates and how to break it. We know roughly how often the great storms come. We know we nearly took one in 2012. The piece that is missing is not knowledge. The piece that is missing is the social will to convert that knowledge into installed hardware and stockpiled spares and rehearsed procedures. The bottleneck is not in physics or in engineering. The bottleneck is in our collective attention. The cosmic forecast exists in part because that attention needs to be re-earned every time a quiet decade passes without the storm we are betting against. There is a strain of fatalism that creeps in here, the suggestion that nothing can be done, that the grid is too large and the threat too rare, and the human institutions too short-sighted ever to act. I do not buy that, and I do not want you to buy it either. Other long-tail hazards have been treated more seriously when the public and the political class began to take them seriously. We have built warning systems for tsunamis after the great waves of the early 21st century. We have hardened buildings against earthquakes in regions where the lesson was paid for in lives. We have built international machinery for pandemic surveillance, however imperfect, because the cost of not having it became unignorable. The pattern is always the same. The hazard is known long before the hardening, and the hardening accelerates after a near miss or a direct hit that finally makes the abstract concrete. The Carrington event is too old to function as that concretizing event for most people. The 1989 Quebec blackout is fading in living memory. The 2012 near miss happened in space, where no one could see it. We are running out of clean lessons to convert into action without paying for them in blackout months. There is a piece of this story that is genuinely hopeful, and it lives in the engineers and the forecasters, and the small policy circles where the threat is taken seriously every day. The Space Weather Prediction Center exists. The spacecraft at the first Lagrange point exist. The research programs that red ice cores and tree rings for ancient storms exist. The studies that model what a direct hit would cost exist. The international cooperation among space weather agencies exists. The community of people who would, if asked, know how to begin the hardening exists. This is not a story about a danger we have never recognized. It is a story about a danger we have recognized and partially mapped and largely failed to act upon, which is, in a strange way, easier to fix than a danger we did not know about. The first 90% of the intellectual work is done. The remaining 10% is the part that requires us to look up from our quarters and our election cycles long enough to fund the work of decades. Part of what we can do individually is not very dramatic, but it is real. Talk about this. Notice the small storms. Treat them as the free warnings they are. Ask your utility, when the opportunity arises, what it has done about geomagnetically induced currents and whether the great transformers in your region are protected. Support the funding of the space, whether research that gives us the hour of warning we have. Vote when you can for representatives who treat infrastructure resilience as a serious priority rather than as a place to cut a few points off a budget. None of these alone change the picture. Together, over years, they do. Because what shifts institutional behavior on long-tail risks is not the engineers alone. It is the engineers backed by a public that has learned to take the threat seriously and to ask the question more than once. This is not a doomsday channel. It is the cosmic forecast, and our job is to look at the sky honestly and to tell you what is there and what is coming, without exaggeration and without denial. Tomorrow's storm is mild. The next great one will not be, and we do not know which decade it lives in. The work between now and then is the work of taking a hazard that has spent the modern era being treated as an abstraction and making it concrete enough to be acted on. The auroras tomorrow night, if you see them, are not just pretty. They are a quiet, gentle reminder that the same physics will, on a date none of us can predict, write a far longer and more terrible story. The reminder is free. The acting on it is up to us. Step outside for a moment, in your imagination, and look at the sky the way our ancestors did. Long before there was a space weather prediction center, long before there were satellites and grids and orbital clocks and forecast indices, there were people standing on this same planet looking up at this same sun and the same sky beyond it, and trying to make sense of what they saw. The auroras that lit up the night skies of 1859 came down into latitudes where they had never been seen in living memory, and people watched them with the only frameworks they had. Some thought the world was ending. Some thought a vast battle was being fought in the heavens. Some thought the polar fires had crept south as an omen of war. None of them had the concept of a coronal mass ejection. None of them had the concept of magnetic reconnection at the front of the magnetosphere. None of them had the concept that an iron core in a transformer in a substation could be saturated by a current induced in the ground by a changing magnetic field above their heads. Because none of those concepts existed yet. Because none of those things existed yet. What did exist was the same star, doing the same kind of thing it had been doing for billions of years before anyone was looking, and will continue to do for billions of years after the last person stops. The sun does not know that we are here. The sun does not know that we have built a civilization out of long wires and orbital clocks. The sun does not know that we have made ourselves dependent on the very systems that its occasional eruptions can disrupt. The sun is a ball of plasma held together by gravity, fusing hydrogen into helium in its core, churning that energy outward through layers of incredible complexity, and venting it as light and as wind, and occasionally as great violent eruptions of magnetized plasma. It has been doing this for 4.5 billion years, give or take, and it will do it for billions more, on its own schedule, indifferent to whether we are watching, indifferent to whether we are ready, indifferent to whether we have built our world in such a way that we will weather what it throws or be broken by it. There is something humbling about that indifference, and I think it is worth sitting with for a moment, because it is the right scale on which to consider the threat we have been discussing. We tend to talk about natural hazards in the language of villains, as if the sun were attacking us or the storm were aimed at us. The truth is more humbling. The sun is not aimed at us. The sun is doing what it does. We happen to live in the path of what it does, on a small rocky planet draped in a thin protective magnetic field. And the way we have arranged our affairs on that small rocky planet has made us much more exposed to certain rare events than we used to be. The hazard is not malicious. The hazard is mechanical. The mechanical operations of an enormous fusion reactor 93 million miles away occasionally produce, as a normal byproduct, the kind of cloud that crossed Earth's orbit in 2012 and will cross it again, on a schedule we do not control and cannot predict precisely, and that we have made ourselves remarkably vulnerable to. There is a different way to look at this, though, and I want to offer it before we close. The auroras you may see tomorrow night are part of a long story. The cave paintings of our most distant ancestors include, in some interpretations, drawings of what may be auroras. The Greek philosophers wrote about strange lights in the northern sky. Medieval chroniclers recorded skyfires and red dawns at midnight, often interpreting them as portents or omens. Indigenous peoples across the Arctic developed entire cosmologies around the dancing lights of the polar night. The auroras have been a part of human imagination for as long as there have been humans capable of imagination, and they have always carried a sense of something larger than us moving in the sky. That sense is not wrong. It is just that the something larger turns out to be a star. When you understand that the lights are caused by particles racing down the field lines of our planet's own magnetic shield and striking the upper atmosphere, the lights do not become less wondrous. They become more so. They become, in a sense, a visible manifestation of an invisible architecture, the bubble of magnetism that protects everything alive on Earth from the constant wind blowing off the sun. The aurora is the sound the shield makes when it is hit. The aurora is the receipt our planet writes for the energy delivered to its doorstep. Every flicker of green you might see tomorrow night is a piece of the sun, decelerating in our sky, giving up its energy in the form of light, and protecting you in the process. The shield is doing its job. The light is the proof. There is a kind of literacy that comes from being able to read the sky that way, and I think that literacy is one of the most valuable things you can carry. Most people walk around in a civilization that is, in deep ways, dependent on the patterns of an indifferent star, and they have no framework for understanding that dependence. They do not know that the timing on their phone bounces down from satellites that fly through a sometimes hostile environment. They do not know that the lights in their kitchen run on a grid that can be disturbed by a magnetic field 8 light minutes away. They do not know that the auroras are not a separate phenomenon from the storms, but the same physics in 2 different costumes. To learn to read the sky is to learn to see the connections between things, between the lights overhead and the wires underground and the machines in orbit, and to hold them all in mind as a single system, a single conversation between a star and a planet that has been going on for billions of years, and that we have only recently begun to listen in on. That conversation will continue. Tomorrow's storm is one syllable of it. The next great storm will be another. The cosmic forecast exists to translate that conversation, day by day, into language that we can act on, and to keep the small storms from being forgotten as quickly as the auroras fade from the morning sky. The small storms are not noise. They are vocabulary. They are the way we learn what the sun can do, with consequences small enough to study and survive, so that, when the large version comes, we are not encountering it for the first time. I want to take you forward in time now briefly to imagine the day after tomorrow, the morning after this storm has passed. Because the most important hours of a space weather event are sometimes the ones immediately following it, when the temptation to file the whole thing away as nothing is at its strongest. By the morning after tomorrow, if the forecast holds, the cloud will have washed past us, and the disturbed conditions in the magnetosphere will be subsiding. The aurora index will be drifting back down from 7 toward the quieter numbers of an ordinary week. The Space Weather Prediction Center will issue summaries of what happened, what the storm actually delivered compared to what was forecast, where the auroras were seen. What reports of disturbance came in from operators of grids and satellites and high-frequency radio circuits. There will be photos online of green skies over places that almost never see green skies. There will be a brief flurry of news coverage. There will be people sharing what they saw with each other across thousands of miles. By the afternoon of the day after tomorrow, most of those people will have moved on to whatever the next thing in the news cycle is. That is the moment the lesson of the storm slips through our fingers if we are not careful. Because the natural impulse in the absence of any obvious damage is to conclude that nothing happened, that the warnings were overdone, that the storm was a non-event. It is the impulse to say, "See, I told you it would be fine." The impulse is understandable, and it is wrong, and it is dangerous in proportion to how widely it spreads. The storm was not a non-event. The storm did what storms of that size do. It pushed real geomagnetic indices into elevated ranges. It pushed real induced currents into real long wires. It pushed real load and reactive demand onto real transformers, which absorbed it because they were sized and protected to absorb it. It pushed real perturbations into the upper atmosphere, briefly degrading the precision of satellite signals, briefly increasing the drag on satellites in low orbit. briefly disturbing high-frequency radio circuits on the sunlit side of the Earth. It delivered, in miniature, a sample of every mechanism we have been discussing. If you are an engineer at a utility or a satellite operator or a power grid coordinator, you treat the morning after as a learning opportunity. A chance to review the telemetry and see how your system responded and where its margins were and what the next, larger storm would do to it. If you are a member of the public, you treat the morning after as the moment to remember what the storm was, not in spite of the fact that it was mild, but precisely because of it. The mildness is the gift. The mildness is what lets us study the mechanism without paying for it. The auroras of tomorrow night, viewed properly, are not a separate thing from the catastrophe of the future. They are part of the same continuum. They are the surface of a deep ocean. They are the audible part of a much longer and quieter and more dangerous song. The temptation, after each small storm, is to listen only to the audible part and forget that the longer song is still being sung. The cosmic forecast exists in part to keep the longer song in mind, to refuse to let the small storms become the entire story, to keep the question of preparation alive in between the moments when the sky reminds us to care. You can do this too. You can be one of the people who, on the morning after tomorrow, does not file the storm away. You can be one of the people who notices that the warning systems worked, that the grid operators did their jobs, that the spacecraft upstream of Earth read the cloud's magnetic field in time for everyone to react. And you can ask, in your own mind and in your conversations, what would have happened if the cloud had been 10 times larger and the field had been pointed the wrong way? You can be one of the people who remembers, the next time someone says solar storms are not really a threat, that we missed one in 2012 by a calendar week, and that the 1989 storm dropped a province in 90 seconds. You can be one of the people who notices, when news of grid upgrades or space, whether research funding comes up in policy debates, that this is the kind of decision that decides whether a future storm becomes a story we tell about a near miss, or a story we tell about a disaster. None of this is dramatic individually. All of it together is how a society learns to take a long-tail risk seriously. The morning after tomorrow will be ordinary. The sky will be blue. The sun will be quiet for the moment. The lights will be on. The phones will work. The money in the bank will still be the right number. The grid operators will go home, and the satellite teams will write their reports. And the auroras will be a memory of a beautiful night, already half forgotten, by the time the second cup of coffee is poured. Nothing visibly will have changed. Underneath the ordinariness, though, there will be a little more data, a little more experience, a little more evidence that the threat is real and the machinery exists to manage it when it is small. The question is whether that data accumulates into action over the years to come, or whether it accumulates into complacency. The slow conclusion that, because nothing has yet broken, everything will continue not to break. Tomorrow, in the late part of the day, a cloud of plasma that left the sun on the 6th of June will arrive at the Earth. If the magnetic fields align for trouble, the storm will reach the strong level the forecasters have warned about. If you are under a clear northern sky, you may see the auroras pushed down to latitudes that rarely see them, and it will be one of the more beautiful things you will ever witness. The lights in your house will stay on. Your phone will work. The grid operators will manage the trickle of induced current the way they have learned to. By the day after, the storm will be a memory and a few nice photographs. That is almost certainly how tomorrow goes. I am not here on the cosmic forecast to tell you to be afraid of tomorrow. I am here to tell you that tomorrow is the easy version of a test we will eventually be given for real. The sun has shown us, in 1859, what it can do. It showed us again in 2012, when it fired the loaded gun and missed us by a week. The physics that paints the auroras is the physics that can collapse the grid. The only variables are the size of the storm, which we do not control, the orientation of its magnetic field, which we cannot predict until it is nearly here, and the timing of the sun's rotation, which is pure chance. Everything else, the wires we have strung, the satellites we have launched, the dependencies we have built, the spares we have failed to stockpile, the hardening we have left undone. All of that is on us. All of that we chose. 93 million miles away, there is a star that gives us light and warmth and the energy for every living thing on this planet, and it has been doing so faithfully for billions of years. Every so often, on its own schedule, indifferent to us, it convulses and throws a piece of itself across the void. Tomorrow, we get the small piece. One day, on a time scale no one can promise is far off, we will get the large one. When it comes, it will find a civilization that wired its entire existence into the one thing the storm destroys, and left itself, year after year, more exposed, not less. The auroras tomorrow night will be lovely. Look up at them if you can. Understand what you are looking at. You are looking at the gentle face of the only natural force on this earth that could, in a single day, take the modern world apart. The question that should keep us up at night is not whether it is coming. It is whether, when it finally does, we will have done anything at all to be ready, or whether we will simply have kept building the target right up until the morning the lights do not come back on. This has been the cosmic forecast. Look up, stay curious, and remember that the same sky that gives you the lights tomorrow is the sky that will, eventually, write the rest of the story.